Good morning. I am Dr. Ravi Medalli, Professor and Head of the ENC Department at Balekundri Institute of Technology, Belgaum. Friends, we have seen last class we discussed the operation of full wave bridge rectifier. As you know, the full wave bridge rectifier, it consists of a step down transformer in addition to the 4 diodes in a bridge configuration along with a load resistance here. The step down transformer, it steps down single phase 230 volts 50 hertz AC supply to a lower voltage that depends upon the rating of the transformer. So, this step down voltage, it is fed to the bridge rectifier here. So, during positive half cycle, the positive half cycle of the input, the potential at this point will be at positive with reference to the lower point. So, therefore, the diode, this diode D1 and D2 will conduct. So, therefore, and whereas the diode D3 and D4 will not conduct. So, therefore, the low terminals are connected to the source terminals through the conducting diode D1 and D2. So, during negative half cycle, so what happens? This is the potential of this terminal will be at negative potential with reference to this. So, therefore, this primary voltage and will induce an voltage, secondary voltage having minus plus potential at the secondary winding here. So, due to this, once again here this diode D3 and D4, they will be forward biased, whereas diode D1 and D2 will be reverse biased. So, therefore, we can replace the diode D1 and D2 by open switch, whereas the diode D3 and D4 we can replace it by the closed switch here. So, therefore, the low terminals are connected to the source terminals through conducting diodes D3 and D4. So, therefore, output follows the input. So, what we get is this output here. So, this is okay. The whatever output you are getting from this bridge rectifier, it is a pulsating DC here. And also we compared the full wave bridge rectifier with the other rectifier, that is namely full wave center tap rectifier than half wave rectifier. Compared to the other rectifier, the conversion efficiency of the bridge rectifier is 81%. Similarly, the center tap configuration is also having 81% of conversion efficiency. As I told you, the conversion efficiency is nothing but it is the ability of rectifier to convert AC into DC. And also we discussed about the ripple factor. The ripple factor is a measure of the AC ripple content of the DC output here. Friends, the ripple factor of full wave bridge rectifier, which is defined as the RMS value of AC voltage to the DC voltage here. So, the ripple factor of full wave bridge rectifier, it is less, and it is less compared to the half wave rectifier, but it is same as the full wave center tap rectifier here. And another one more important parameter we compared, that was PIV rating. It is also called as peak inverse voltage rating here. Peak inverse voltage means it is defined as the negative maximum voltage that can be applied across the device or diode without damaging it. So, therefore, in case of half wave rectifier, so the PIV rating of the diode used is Vm. However, in case of the center tap configuration, it is 2 Vm. Alright, and as far as the full wave bridge rectifier is concerned, the PIV rating, it is once again Vm. So, as you know that the PIV rating increases, the cost of the diode used in the rectifier configuration will also be more, and also the size, that is bulkiness of the diode that is used in the rectifier will also increase. So, this is the one important limitation of the center tap configuration. So, the one other these are the few important parameter we considered. One is the conversion efficiency, ripple factor, PIV rating. But however, the full wave bridge rectifier, right. So, the one limitation of full wave bridge rectifier is that it uses the two diodes while conducting. So, during positive half cycle, as you know that the diode D1 and D2 will conduct. During negative half cycle of the input signal, diode D3 and D4 will conduct together. So, at any instant of time, two diodes will conduct together, and therefore, so this will result voltage drop of 1.44 volts. So, whenever we are converting a small AC voltage into a DC voltage, this voltage drop, it will play an an important creates an important problem here. So, therefore, for a lower AC voltage, the full wave bridge rectifier cannot be used, since there will be a voltage drop of 1.4 volts compared to other half wave rectifier and full wave center tap rectifier here. Even though the bridge full wave bridge rectifier so has merits or advantages over other rectifier with regard to conversion efficiency, then PIV rating, then ripple factor. The one limitation of full wave bridge rectifier is that the voltage drop of the diodes, it will be 1.54 volts if I consider diodes used are silicon diodes here. And also we have seen the regulated the capacitor filter, we discussed about this. So, here this particular block diagram shows the rectifier, the output of that it will be fed to the capacitor here, and across capacitor resistance, load resistance is connected, and across this RL, and we are taking out the output here. And friends, here you can see that, so without this capacitor we would have got a pulsating DC output like this, because as you know that this is this rectifier, it must be either the full wave, if I consider full wave bridge rectifier, then the rectifier will conduct both the half cycle of the input signal here. So, therefore, here what is happening, the capacitor, it will charge during so, and it will charges, and during when this, then it will decays here till this point, and once again it will start charging here to the peak value, and once again once it reaches the VM value, once again it will able to decay it. So, using, as you know that the reactance of the capacitance, it is 1 by 2 pi Fc. So, that means the Xc is inversely proportional to the frequency. For AC signal, the frequency usually it is 50 hertz. So, the capacitive reactance of the capacitor will be more here. So, therefore, it will oppose the AC signal, but allows the DC signal here. So, it allows the DC signal, because the capacitive reactance of the capacitor for AC signal is less, whereas the capacitive reactance of the capacitor is more for DC here. Therefore, capacitor, it blocks DC, whereas it allows only AC signal. So, therefore, finally what the output we are getting is this output, whatever you can see here, that is overlap of the pulsating DC. And this particular session, you will be able to understand what is DC power supply, and also you will come to know the differences between regulated and unregulated DC power supply, and also the construction and working of Zener diode also will be explained, because as you know that the Zener diode will be a part of a voltage regulator, and at the end of the session you can see the application of Zener diode as a voltage regulator here. DC power supply. The basic purpose of DC power supply is to provide one or more fixed voltages to the working circuit with sufficient current handling capacity to maintain the operating conditions of the circuit here. There are two types of DC power supply. One is called as unregulated DC power supply. The second one is called as the regulated DC power supply. In case of the unregulated DC power supply, the output of the supply changes whenever there is a change in the load current, and also whenever there is a change in the source voltage. However, in case of the regulated power supply, the output will be maintained constant irrespective of variations in the load current or the variations in the source voltage. And you note that the regulated power supply, it is very much required for all critical electronic applications, and also you know that all the semiconductor devices requires a regulated DC power supply, and therefore this particular regulated power supply, it is plays an important role. And also we have seen here the regulated DC block diagram of regulated DC power supply consists of a step down transformer. Here what we have is a step down transformer, then a rectifier, then we have a filter, and the final block of this regulated DC power supply will be a voltage regulator here. So the input to the step down transformer, it will be single phase 230 volts 50 hertz AC supply, and output will be a step down voltage what we get depending upon the rating of the transformer here, and this voltage, it will be acts like a input to the rectifier. The function of rectifier, it converts the fixed AC into fixed DC here, right. But what we expect is a continuous DC, but what we are getting is here at the output of the rectifier is a pulsating DC. So therefore, in order to remove the AC content of the DC supply, a filter is being used. This filter, it removes the AC ripples of the DC output of the rectifier, and it gives almost a continuous DC here. So therefore, thereby increases the ripple factor. So output of the filter, it is being fed to the regulator, that is nothing but the voltage regulator, as I told you that. So this regulator is nothing but it is a regulated this is regulator which regulates or which provides a constant output irrespective of variation in the input source voltage or the changes, that is anything is taking place in the load current. So finally we will be able to get a continuous constant DC output from this regulated DC power supply. So it may be plus 5 volts or minus 5 volts or 30 volts or anything could be generated, right, using this regulated DC power supply. Friends, we have seen that, right, we know that a load means anything which we connect across the output of a circuit here. Whenever the load is connected, loading effect is produced. Due to loading effect, the output voltage drops, that means it decreases, and this loaded voltage we call it as apparent voltage. And you please note that the apparent voltage is always less than the true voltage here. There are two terms we need to know when we discuss the voltage regulator. One is called as the load regulation. It is being defined as the change in output voltage when load current changes from minimum to maximum here, and the other term, that is line regulation here. It is being defined as the change in the output for a specified range of line voltage. Right? You please note that the load means it refers to the load resistance RL. So whereas line means it refers to the input voltage, that is the line voltage that is being fed to the regulator here. And also the voltage regulator has two important protection circuits. One is called as the over voltage protection, the other one it is called as the overload protection here. So this overload protection, over voltage protection is means whenever the line voltage, that is input voltage, is abnormal or exceeds the value, or it might right below the input value, the specified value, then this it will become switched off. So similarly, the voltage regulator, it has got a overload protection, that is whenever load current exceeds the limit, this particular voltage regulator, it will be switched off here. So friends, you know that a Zener diode, it is being used as a voltage regulator. So prior discussing the voltage regulator in detail, we need to know about some important information I need to share amongst you about the Zener diode. The Zener diode, it is a special PN junction diode. Alright. So the construction is similar to the conventional, that is a normal diode. It's similar to that, right, like the normal diode, it has got a P layer, it has got a N layer, and whenever these P and N layers are joined, so that will create a depletion region, right. So depletion region means what? It is the region which is depleted of the charge carriers. That means it contains only immobile ions which are fixed in position here. and because of this depletion reason there will be a potential barrier exist across the junction, that is, and which will block the movement of the charge carriers across, that is between P and N layer. So, and also you know that the depletion layer width, it depends upon the doping intensity of the P and N layer. So, if the doping intensity of the P N layer is more, then the width of the depletion layer will be less. And also we noted earlier in last class that whenever the doping intensity of the P-N layer is more, that is less, then the depletion width will also increases. So therefore, for heavily doped P and N type of semiconductor, the width of the depletion layer will be less, and similarly correspondingly, consequently what happens, the barrier potential will be less. Whereas for lightly doped P and N type of semiconductor, the width of the depletion layer will be more, and accordingly, so we will have a higher barrier potential here. So please note that friends, the Zener diode, unlike this the normal diode, it is made by two heavily doped P and N semiconductor, right, and it's this doping concentration that will decide the one important parameter, that is called as Zener voltage, or also it is called as Zener knee voltage here. And this particular device, that is Zener diode, it is named after the scientist called as Clarence Zener, who discovered this property here. If we look into the construction of the Zener diode is a type of diode that permits current not only in the forward direction like normal diode, but also in the reverse direction if the voltage is larger than breakdown voltage known as Zener knee voltage or Zener voltage. That means unlike the like normal diode, this Zener diode, it conducts the current in the forward direction, but however unlike the normal diode, this Zener diode, it also conducts in the reverse direction, because as you know that the normal diode, since it allows the current to only to flow from anode to cathode, so it is being used as the as a rectifier. That is one important application of the diode, normal diode. Whereas this in this case, since it not only this Zener diode not only conducts the current in the forward direction, but also it conducts in the reverse direction whenever the reverse voltage exceeds the breakdown voltage called as Zener knee voltage or Zener voltage. So this important application. So whenever, usually you know that the Zener diode is being operated in the reverse direction. So whenever it is being used as a reverse direction, it will be able to provide a constant output voltage across it. This particular slide shows the symbol of the Zener diode, and whatever the arrowhead you can see here on the Zener diode symbol, it points in the direction of the forward current when the diode is forward bias. That means forward bias means anode is connected to the positive terminal of the battery, whereas cathode is connected to the negative terminal of the battery. Then the Zener diode will be forward bias, and then the current will flows from anode to the cathode here. So that will be the current direction flow. It is indicated by this arrow mark here. The Zener diode, it is normally operated in the reverse breakdown, and the current direction is then from the anode to cathode here. So unlike the normal diode, that is normal conventional diode, it is being operated only in the forward direction, and therefore it cannot be operated in the reverse direction. So therefore the normal or conventional diode can be used as rectifier. However, the Zener diode, it is usually being operated in the reverse direction. So therefore that too in the reverse breakdown region, and therefore so it can able to provide a constant output voltage here. So this particular this figure you can see it is a commercially available Zener diode here, and whatever a small ring you can see this side, so on the bottom side of this Zener, that represents the cathode here. So then the other end will be anode here. And if we need to know, before understanding the concept of the voltage regulation, we need to know three parameters. One is called as Zener voltage, the second one is power handling capacity, then third one is called as the tolerance of the Zener voltage here. Zener voltage, so the normally the Zener voltage, it ranges from 3.3 volts to 75 volts here, and the power handling capacity of that is a popular Zener diode ranges from, right, so which are available in the market are quarter watt, then half watt, then we have 1 watt, 5 watt Zener, 10 watt Zener and 50 watt Zener here. Okay. And as far as the third parameter is concerned, parameter of the Zener diode is concerned, the tolerance of Zener voltage, that is most popular tolerances available are 5% or 10% here, right. So this is the three important parameters of the Zener diode. When we think of designing a voltage regulator using a Zener diode, we need to know these three parameters. One is Zener voltage, power handling capacity, and then the tolerance of the Zener voltage here. Friends, this particular slide shows the forward characteristics of the Zener diode. What it looks similar to the forward characteristics of Zener diode. It looks almost similar to that of the conventional diode or normal diode. So therefore, in the forward region, the Zener diode acts like a regular silicon diode with a 0.7 voltage drop when it conducts here. Okay. So therefore, here you can see that this is the axis representing the forward voltage, and this y axis it represents the forward current here. And whenever until and unless this forward voltage exceeds a voltage called as threshold voltage or cut-in voltage, the Zener diode do not conduct. Once the forward voltage exceeds the threshold value of or threshold voltage of the device, that is Zener diode, then a large current will start flowing, that is here. So the threshold value, it depends upon whether the Zener diode is made up of silicon or germanium. If it is a germanium, it then will be having threshold voltage of 0.3 volts, whereas in case of the silicon diode, it will be 0.7 voltage drop. This particular slide shows the reverse characteristics of the Zener diode. Okay. So unlike this normal diode, because in the normal or conventional diodes, they will never be operated in the breakdown region, right. But the Zener diode, they can be safely operated in the breakdown region, and it is because of this reason here. So the Zener diode can be used as the voltage regulator here. Friends, you can see that it consists of in the earlier slide you have seen the forward characteristics of the Zener diode. Okay. So finally, the Zener diode, if you look into the VI characteristics of the Zener diode, it consists of three regions. One is called as the forward bias region, wherein once until the VF reaches the threshold voltage, the current will be 0, and once the VF exceeds the threshold value, then current increases suddenly there. So whereas apart from the forward bias region, this Zener diode has got two more regions. One is called as the reverse bias region, and another is called as third region is called as the Zener breakdown region. And whatever you can see here from 0 volts to the VZ, that region we usually call it as the reverse bias region. Once the reverse voltage exceeds this Zener voltage or Zener knee voltage, then there will be a breakdown. A large current flows through the Zener diode and providing a constant output across the Zener here. So therefore, in this particular, whenever the Zener diode it is in the breakdown region, we usually use it as a voltage regulator here. So therefore, conventional diodes, they will be never operated in the breakdown region, right. So that means if you operate the conventional diodes in the breakdown region, so a large current flows through this, and which will damage the conventional diodes. However, in case of the Zener diodes, they are manufactured in such a way that whenever these Zener diodes are safe, that operated in this breakdown region, they can be safely operated without any problem, alright, without causing any destruction to the device here. And also you can know that, okay, in the reverse direction, okay, that is, as I told you, that the Zener diode has got 3 regions. If you look into the VI characteristics of this, it has got 3 regions. One is forward bias region, that is, okay, in the first quadrant of the VI characteristics, and then the reverse that is bias region or reverse direction. This is reverse bias region, and another is called as the Zener breakdown region. The between the voltage 0 to Vz, that is Zener voltage or Zener new voltage, the whatever region is there, no, that we call it as the reverse bias region. And in this region there will be a small leakage current flows through that, which will be in terms of microamperes. Okay, so whenever this Zener voltage, okay, or reverse voltage reaches the Zener voltage, okay, suddenly a large current flows, that is freely, and this ability gives a greatest application to the Zener diode. Therefore, we make use of this Zener diode as the voltage regulator here. Now let us see what is Zener effect here. The width of the depletion region is very less at high impurity concentrations, okay. Because why it is less, the width of the depletion region? Because both P and N regions of the Zener diode are heavily doped. So consequently what happens? The depletion width will be less. As I told you that whenever the depletion region width goes down, accordingly the barrier potential will decreases here. So therefore, whenever the width of the depletion region very less, right, at high impurity concentration, it results in a high electric field intensity. So this high electric field intensity will be sufficient to break the covalent bonds, and therefore once these covalent bonds are broken, that will release the free electrons, and this release of, okay, free electrons, okay, that will result in the formation of a large number of electron hole pairs, and therefore this results in a sudden increase in the reverse current, and this is known as the Zener effect. That means, as you know that in the Zener diode, both the P and N semiconductors are heavily doped, and naturally the width of the depletion region is very less, and this will gives rise to very high electric field intensity at the depletion region, and this high electric field intensity is very much sufficient to break the covalent bond, and that will, okay, results in the release of, okay, increase of the electron hole pairs, and that will, okay, results in the formation of large number of electron hole pairs, and therefore that which in turn results in the sudden increase in the reverse current. This is the, okay, basic Zener diode circuit. That is other way we can say that the voltage regulator circuit using Zener diode. What it consists of? It consists of the supply voltage, that we can call it as V1, and the supply voltage, output voltage, we, okay, denoted it as V2 here, which we taken across the Zener diode, and we have a small series resistance or resistance in series with the Zener diode here. And always it should be noted that the current through the Zener, it will be never be allowed to, okay, less than 5 milliampere. If it is, once again, okay, if you are allowing the Zener current, Zener diode current, or the current that flows through the Zener current to go, it decreases below 5 milliampere, then the Zener diode will not be able to act like a voltage regulator. That point you should be able to note on here. And this whatever current you say, what a current that flows through the circuit, it is because of the, okay, it is given by V1, that is the input voltage, or we can call it as Vs also, then V2, that also called as Vz or V0. So therefore divided by R here. So therefore current I, that is current flowing through the voltage regulator circuit, it is given by the ratio of difference between input voltage and output voltage divided by the series resistance. So therefore the current, this whatever current as that is shown, no, that should be, or never be, always it should be kept greater than 5 milliampere. So therefore the R value, it should be okay, it should be selected in such a way that always this, okay, current that is flowing through the device never be allowed, right, below 5 milliampere. If it is allowed, once it is allowed to goes beyond this 5 milliampere or below 5 milliampere, then Zener diode never will be able to work as, operate as the voltage regulator here. So this is what is shunt, whatever circuit we had discussed, okay, that is nothing but the shunt shunt Zener regulator here, because here, since the voltage source voltage, it is in series with the R, and R will be in series with the Zener diode. And please note that the Zener diode will be always operated in the reverse direction. That is why the cathode will be connected to the source voltage, anode, okay, will be at it will be connected to the this terminal here, okay. So always please note that the Zener diode will be operated in the reverse direction. So because whenever the Zener diode operates in the reverse breakdown region, this will be able to provide a constant output voltage that is called as Vz or V0 here. So this most basic Zener diode regulator circuit, okay, or shunt Zener regulator circuit, it consists of a single Zener diode and a resistor here. The Zener diode, okay, provides the reference voltage, but a series resistor must be placed to limit the current into the device. Otherwise a large amount of current would flow through it and it could destroy. That is what I told you. The value of the series resistance should be selected in such a way that the current through the device, right, should be limited, right. Otherwise, what happens if we allow a large current to be to flow through the Zener diode, then that current might destroy the Zener diode here. So in case of the shunt Zener regulator, the value of resistor, that is series resistor, that is resistor that is being used in series with the Zener diode, should be calculated to give the required value of the current for the supply voltage here. So as you have seen that the value of resistor, it will decide the current that is flowing through the device, because as you have seen, I is nothing but it is a ratio of the source voltage minus the output voltage divided by R here. So I is determined by R, since because these so typically most low powered leaded Zener diode have maximum power dissipation of 400 milliamperes. That is what is being specified here. So this is what is the minimum power handling capacity, right. So maximum power dissipation of the 400 milliwatt it can be allowed to flow through the Zener diode. Otherwise, if we allow the right power dissipation to exceed this value, so once again it will cause heavy damage to the device here. So ideally this circuit, whatever the shunt Zener regulator circuit is there, should be designed in such a way that it should be able to dissipate less than about half this value. Half this value means half of the 400 milliwatt of value, but to operate correctly. And also it should be okay noted that current into the Zener diode should not fall 5 milliampere, should not fall below 5 milliampere. Otherwise what happens, the Zener diode cannot able to regulate the voltage correctly. Now let us go to this particular, okay, circuit here. Then let me switch over to the Zener diode circuit. What do we have here? We have shunt, okay, the that is regulator, voltage regulator, you can say it is. Shunt means in parallel here. Here we got an input supply, right. This is called as, I can call it as Vs, and then we have a resistance here in series with the supply, okay, and then we have a Zener diode. It is always mounted in such a way that it is operated in the the reverse breakdown region. Therefore it will be okay, this cathode, this is the cathode, what we can see here, this is the cathode, it is connected to the positive terminal, whereas anode is connected to the negative terminal. So definitely this particular resistance will be in reverse direction. This resistance I can call it as R here, and then what we have, this is we take output across this the Zener. So now, and also let us denote the current, that is the input current that is flowing through this, and this current whatever that flows through the current, the Zener diode, we call it as IZ, and let us have one a load resistance here. Usually it will be a resistor, and across this we will take the output here. It will be once again this. So this current, what we can see here, this is nothing but the IL current here. So if you apply KCL here, Kirchhoff's current law, at this point, what you can see, IS applying Kirchhoff's current law at this point terminal, let us say this is point A. So what you get here, you get it as IS equal to IZ plus IL here. We are assuming that we are right, this Zener diode, it is in the breakdown region. So to have this Zener diode in the breakdown region, we have chosen this Vs in such a way that Vs will be more than the Zener voltage, that is called as the Zener knee voltage or Zener voltage. Simply it can be called as Zener voltage. Now what is the job of voltage regulator? It should be able to provide a constant output, let us say constant V0, irrespective of the variations in the source voltage, or the load or RL. You can see it as RL here. So whenever there will be a variation take place in the Vs, right, or RL, this shunt voltage regulator should be able to provide a constant voltage. Now let us assume that the Vs increases. Now assume that RL is kept constant here. So in case of RL is first case, RL is kept constant, and so Vs increases. So when Vs increases, what happens? Whenever this Vs increases, so this leads to increase in the source current. As you know that this Is, that is source current, is nothing but sum of Zener current plus IL here. So what happens here? So Is, you know that Is is nothing but Iz plus IL. So we need to keep this IL constant. So therefore whenever Is increases, so Zener current will also increase correspondingly, so as to keep IL constant here. So when IL is constant, RL is constant, therefore what happens? V0 will be a constant here. Are you getting my point? So here please, I will repeat here, whenever there is an increase in Vs here, so that will result in an increase in source current. As you know that source current is nothing but a summation of Iz plus Is. So whenever Is increases, so therefore Is should be allowed to increase in order to keep IL constant here. Whenever IL is, so when we say that IL is kept constant, so what is V0 here? V0 is nothing but it is IL into RL here, is it not? So when IL is, we say, when I say that IL is constant, RL is constant, so then V0 will be constant. So therefore the shunt regulator, voltage regulator, will be able to provide a constant output voltage irrespective of variation in the source voltage. Now for the second case, if I assume that, so second case, if I take it, in case the Vs is constant, okay, Vs is, this is kept constant here. Now there will not, I am assuming that there is no much fluctuations or variation in the source voltage, okay, whereas right RL is decreases. Now RL will decrease. When RL decreases, right, what should happen? IL should increase. Okay, when RL decreases, so I should allow the IL to increase here. So therefore, IL automatically increases. When load current increases, what is load current in terms of IS and IH here? So that is given by this equation, IS equal to IZ plus IL. Therefore, here IL, okay, when IL increases, so therefore naturally IZ should be decreases, okay, IZ should decrease, that is current flowing through the Zener diode should be, right, should decrease here. So therefore, in this case finally what you can get is V0 is constant here. Similarly, whenever there is an increase in the IL, that will result in the, right, IL decreases. When IL decreases, okay, so what is IS here? IS is nothing but IZ plus IL. So in order to keep IS constant, so IZ should increase here, and therefore this will maintain the output voltage across the Zener voltage constant here. So that is, now let us see, okay, that's what is given here. So in case of the, okay, constant RL, right, so how the circuit, they will be able to stabilize the output voltage. When Vin increases, so what is happening there? So IS increases, that is, so when source voltage increases, source current increases. So therefore IS, you know that it is summation of IZ plus IL, therefore IZ is increases, right, to keep IL constant. Therefore the difference Vn minus Vz increases, and Vz is nothing but V0, that is that will be constant here. Similarly, other case if I take, whenever Vin decreases, Is decreases, right, when Is decreases, so Iz also decreases to keep IL constant here. So therefore the difference of Vn minus Vz decreases, that is mainly to keep Vz, or that is output voltage constant here. That is what is given, Is is equal to Iz plus IL here. So other case, that is when Vn is constant here, okay, how the circuit will be able to stabilize the output voltage? When RL increases, so IL decreases here, but Is has to be kept constant here. So therefore Iz has to increase here, that is mainly to keep output voltage constant. Similarly, here in other case, if I take, if in case the RL decreases, so when RL decreases, the IL increases, okay, and to keep Is constant here, so what happens, Iz should decrease here, and that will allow the to keep output voltage constant here. So that is what given in the form of the equation here, Is equal to Iz plus IL there. Now friends, let us see, okay, one problem, okay, based on this voltage shunt regulator, that is 5 volts stabilized power supply is required to be produced from a 12 volts DC power supply input source. The maximum power rating Pz of the Zener diode is 2 watt. Using the Zener voltage circuit, right, calculate maximum current flowing through the Zener diode, the minimum value of the series resistance Rs, the load current IL if load resistor of 1K is connected across the Zener diode, and the Zener current Iz at full load. The first case, first one, the maximum current flowing through the Zener diode, it is maximum current is given by the Pz divided by the Vz here. Given Pz, that is power dissipation of the Zener diode, is given as 2 watts, and Vz, Zener voltage, is given as, okay, 5 volts. So therefore we will get maximum current that can be allowed to flow through the Zener, it is 400 milliampere here. The minimum value of series resistance, as you know that already I told you that Rs, okay, it is nothing but ratio of Vs minus Vz, that is input voltage minus output voltage divided by Iz here. Given source voltage is 12 here, the output voltage, right, we are need to provide a constant voltage, output voltage of 5. So therefore, and IZ is given as what we calculated as 400 milliampere here. So this gives you gives you 17.5 ohms as the series resistance there. Then the load current, okay, IL, if a load resistor of 1 kilo ohm is connected across the Zener diode. So IL is nothing but what the output voltage, that is V0. V0 is nothing but Vz here, okay, divided by the RL here. That it is given that Vz is 5 volts here, okay, and RL, value of RL is 1 kilo ohm, what we are that is given. So this gives rise to 5 milliampere there. So then we are asked to calculate the Zener diode current IZ at full load here. So therefore, in this case IZ is nothing but IS minus IL, because you know that IS equal to IZ plus IL here. From that we will get IZ equal to IS minus IL. We have calculated IS is equal to 4 milliamp amperes, and IL, that is the load current, okay, that is calculated is 5 milliampere, and therefore we get 395 milliamperes here. So finally, to conclude, here we are we discussed, okay, we compared had a comparison between the regulated and unregulated power supply, and how, okay, and also we have seen the construction of the Zener diode and the both forward as well as the reverse characteristics of Zener diode, and how the Zener diode is always preferred to be used in the reverse bias mode in order to provide a constant output voltage. So therefore, why the Zener diode will be made use of the voltage regulator. Thank you.